Hello steel friends. In this video I want to cover the big 5 stability requirements that we need to include in our analysis if we're going to design using the direct analysis method in correlation with AISC Chapter C. So I know we talked about this in class and we got some of the notes down, but I figure I'd cover all the notes and in case you didn't get a chance to get the notes written or if they're not quite complete yet, please feel free to bring your notes out and we'll complete them together here in this video. So before we get started, we say in stability design we have to consider the effects of the following, right? And there's this big paragraph here in Chapter C1, and basically it has A through E mentioned. And we're going to hit each of those, but I do want to draw your attention to the last paragraph. It just says that any rational method of design that considers all of the listed effects is permitted. Okay, and so I think that's the key. We need to make sure that we're being rational when we do our analysis and make sure we, account for A through E accordingly. So what are A through E? Well, first we need to make sure our analysis is capturing all the flexural, shear, and axial deformations in the system that will contribute to the displacement of the structure. We need to make sure our analysis captures any second order effects, so this is P little delta and P big delta. We need to make sure geometric imperfections are modeled, that stiffness reductions due to inelasticity are included, and lastly that we account for any uncertainty in strength and stiffness. So how did we used to do this? Well, what was common was the effective length method, and basically in the effective length method we say that in our analysis equation or our design equation, here I just have axial force, but it could be shear or moment. In the effective length method, we say that P sub u, and I need to take my shapes off there. We say that P sub u is determined from a first order elastic analysis. Not including these big 5 stability requirements. What does that mean? Well, that means then when we go to the other side of the design equation in P sub n, we better include this somehow. And so in the effective length method, when we determine P sub n, or the nominal capacity, this is determined using a effective length factor, capital K, from what we call the alignment charts in the manual, that I would say indirectly incorporate A through E. All right, so that's great. As long as we're incorporating them. But we do want to caution you that the alignment charts have some specific rules. They were developed for some specific cases. And so just you need to make sure that in your analysis that you're meeting the requirements of the alignment charts or making the appropriate modifications to that K factor. In the direct analysis method, we do it a little bit different. Here, now we determine P sub u from a second order analysis on the deformed shape of the structure, including loss of stiffness effects. and A through E. Okay, so if we include all 5 of these items, then we do that on the left side of our design equation, and then when we go to compute the nominal capacity, we're allowed to just use a K value, an effective length value of 1. Okay, so we see if we do a more sophisticated analysis here, we have maybe a little bit simplified design. When we calculate our strength, we can use K equal to 1. All right, so what are these 5 requirements? So let's hit them one at a time. So first we say that flexural shear, axial deformations, and all other deformations have to be considered. Okay, and so I would say that this is easily handled by most commercial structural analysis software. All right, so all of these softwares have the capability of accounting for all of the deformations in the system. A couple of things to point out is you probably want to make sure that your software applies all the loads simultaneously. And the designer must include any significant component or connection deformations not input into the software. All right, so usually in software, right, we connect our columns and our beams together, but if we have a very flexible connection, the designer has to do something there where at that connection to make sure that deformation's accounted for when we do our analysis. But otherwise, the software will pretty much take care of item A of the big 5. When we move to item B, we talk about second order effects. And here I'm going to emphasize we want to do equilibrium on what we call the deformed structure. So what is the deformed structure? Well, we have 2 types of deflections, and that's little delta and big delta. So first, when we talk about P little delta effects, this is basically kind of the member, extra deflections on the member level. So in order to understand this, I want to consider the following column, right? It's pinned on both sides, and it's got... If we put a horizontal load in here, so we put in some sort of load, and let me put this load in, orange, if I can find orange. I'll put it in magenta here. All right, so if we apply this load horizontally, and I'll just call this load Q. Here I want to sketch the moment diagram. So this is going to be the moment diagram for the structure. So we see we have Q in the middle, point load, right? It should lead to a triangular moment diagram, value of which is going to be QL over 4, if we remember structural analysis correctly. And this is ultimately going to lead to a deflection on our beam, right? So our beam is going to be curved something like this, and this will lead to an initial deflection here, and I'm just going to call this delta 0. And if we recall, right, delta 0 should be the load QL cubed over 48 EI. All right, so this all from structural analysis 1, right? But now what happens if we apply a vertical load P? Okay, so now we're applying a load P to the column in the vertical direction. Well, we see that if we apply the load to the deformed structure, so we already have this deformation, this delta zero, that at the middle here, if we did a equilibrium, we would see we pick up an additional moment, right? So I just want to jot this down. What happens if P applied after Q? Well, we pick up an additional moment, delta M, P times whatever delta zero is. So P times delta zero. Okay, and so this extra moment causes our moment diagram to shift out a little bit. And because the deflection's kind of cubic, we would have some sort of curved moment diagram where this value here, the additional here, this is delta M. Okay, so this is one way to think about it, right? So we did both of those. But now, what if we apply P and Q at the same time? So I'll say either at the same time or just gradually. Well, what happens is that each increment, as we apply a little bit of a load P, not only are we going to pick up this extra moment, but we're also going to pick up a little bit extra displacement, right? And we can keep doing this and keep doing this. And so really, if we apply P gradually, as we pick up this extra moment and get extra deflection, we're going to cause this moment and the deflected shape to shift out just a little bit further than the blue line. So we really end up out here. And this value here is what we need for our design, right? So this needs to be our ultimate, factored moment that we use. Not the linear, not just from Q, not just the delta plus the delta M, but the value when we apply these gradually. Okay, so just kind of to make our notes complete, we'll just say we have to keep updating delta. And so we can represent that now as our delta M is going to be P times whatever delta is at a given time step. And we'll increment these time steps all the way up to we get to the total load applied to the structure. Okay, so that's how you can understand P little delta effects. And so hopefully if you have any questions, you can come find me. All right, now we have also not just these member imperfections that lead to additional displacements, but we also have system imperfections that need to be accounted for. So, and that's going to be the P big delta. Okay, and so when we look at P big delta, right, I want you to think about, besides this, we have to do the sway of this frame, okay? And so this is an unbraced frame or a moment frame. And so imagine we put the load here and we have this force. So we can imagine this frame is going to shift over, maybe a little bit down due to the weight. And so and we kind of get a deflected shape that looks something like this. Right. So this piece has now shifted over due to this laterally applied load, mount delta. Okay, and so this is the side sway of the frame, or what we say P big delta. So as we apply horizontal loads, we're going to pick up not just individual member effects, but we're going to pick up these large effects. And then if we did this gradually, right now these vertical loads, these vertical loads here in orange, are not on this frame, they're on this displaced frame that are not over the supports, and so that creates even more drift, right? So we're going to get even more drift as we apply our vertical loads on a laterally displaced system. Okay, so our equivalent like column, if we just look or isolate column AB, right now we have this column and we're applying our load, whatever axial force we apply to column AB is now shifted over, and we need to account for this, delta that's occurred at the top. And that's going to give us an additional moment, right? Additional moment. Increased moment in the column of P times some sort of deflection. So increased moment in column, I'll just say, due to story drift. All right, and this is not just related to, because we have this lateral load. We want to recognize that even if we just have an asymmetric load, so if we apply a load not in the center of the frame or not over one of the columns, something like this is going to lead to a little bit of a side sway of our frame, just because the load and boundary is not symmetric. All right, so how do we capture these P delta effects? Well, we can capture them by performing what we call a nonlinear analysis. So basically, in order to solve for m sub u in total, we should run what we call a second order analysis. And this, again, will apply loads in increments updating the structure geometry between load steps. Thus allowing additional load to be applied to the deformed structure. All right, so a lot of commercially available software can do this. This is not a problem. I would say that typically the designer needs to just, I'll say, check a box, click a button, or turn this feature on in the analysis program. All right, so this now, if we just make sure we run a second order analysis in our program, then we don't have to worry, and we've now captured element B of the big 5 requirements. All right, so that leaves the last 3 to be discussed. So the last 3 are C, D, and E. So C requires geometric imperfection. So we know that we can't be perfect in our setup of our frame, and so that's going to lead to both system imperfections and then member imperfections. Okay, so system imperfections, we need to account for this in our design, and we look to AISC, the code of standard practice. for out of plumbness of a structure. Okay, and their standard code of practice is that delta 0 is L over 500, or the length of a column over 500, okay? And so what does that mean? That means that if we return to the previous page, right, if we were designing this frame that's shown, this unbraced frame, well, not only might we have horizontal loads and gravity loads, but when we set this up, that basically this first column might be shifted sideways, and this amount that we shift it is our delta 0, which would have to equal the length of the column divided by 500. Okay, and so that just means that, you know, we can't get things perfectly straight in real life. In addition to this, we need to capture our member imperfections. So when a beam is rolled at the steel mill, it can't be perfectly straight either. So our member imperfections, we also look to standard practice values, and basically the out of straightness allowance that we typically incorporate would be little delta 0 over L, you know, is going to be the length of a beam or length of a column over 1,000. And so this is just accounts for manufacturing imperfections. All right, so we need to make sure we include these in analysis. Now, primarily, we are going to need to incorporate the system imperfections. And I just want to make a note here that, so make a little note that we don't necessarily have to incorporate the member imperfections. Add an R there to imperfections. If we design using Chapter E. So if we design, which we will be doing in this class, so if we design using AISC Chapter E, then our column curve equations already account for member imperfections. Okay, so that means when we do our analysis, all we have to worry about are the system imperfections. All right, moving on to item D, stiffness reductions due to inelasticity. And so if we reference our manual, we'll see that we can do this by 2 items. So 1, all stiffnesses should be taken as 0.8 times the nominal. So this is all stiffnesses, so this doesn't matter. Flexural, axial stiffnesses, shear, whatever have you. So as we input our properties, this will best be handled by, you know, using 0.E in our analysis. So to do the stiffness reduction, when we define our material properties, we're only going to use 0.8 times the elastic modulus, and that will account for some reductions due to inelasticity. The other thing we need to do, and so I'll put an and over here, okay, so we have to do both of these. We also need to reduce all flexural stiffnesses by a tau beta factor. So all flexural stiffness should be taken as 0.8 tau B times the nominal. All right, so if we want to do this, we can either directly use the tau equation in AISC, which is found in Chapter C 2.3, But to do this equation, we actually need to run like a first order analysis and then, figure out what the axial forces in these different flexural pieces are, and then come back and change each of those members individually. An alternative that we will use in this class, we can just say we can take a close approximation of tau b by using the tangent modulus theory. And so instead of using E at all times, we will use the tangent modulus, or E sub t, and we'll see that this is available in the software we're talking about in MassTan 2. So if you're working on the project, you would want to input this with ET rather than just E. All right, and so that's pretty much how we account for that. And so in terms of, this now means we're kind of moving towards not just a geometric nonlinear analysis, but also a material nonlinear analysis. And what we mean by that is that we have an analysis that uses a model of stress strain for the steel that accounts for yielding, or at least for partial yielding, of a member. All right, and the last item of the big five, E, is the uncertainty in stiffness and strength. And this is all this means is we need to account for uncertainty in stiffness and strength. So how do we do that in practice? Well, we use our LRFD methodology. So we just need to make sure that we use the factored loads. So in our analysis, we're using factored loads. And when we come up with the member nominal strengths, we're going to reduce the strength by our phi factors. So we need to factor our loads and reduce strength by phi. And so just to recap here, as a designer, we're going to use a second order analysis. With our LRFD load combinations and compare to